So here we have a light panel from the Millennium Falcon. However, it's not working because the battery really needs a jump start. Thank you. So now that we're jump started, we can see that the power source we're getting, or the EMF, is 9 volts. Also, the resistance of each one of these light bulbs, or resistors, you can use those terms interchangeably when you're working on these circuits, is 4.5 ohms. So I'll just say all the resistors, all 4 of them, have a resistance of 4.5 ohms. So now we want to go through and we basically want to solve the circuit. We want to find the current through each part, the voltages across each resistor. And so to do that, we're going to have to replace the resistors here, not literally physically, but in terms of writing it out. We're going to write multiple resistors as single resistors to simplify our calculations. So what I would do here is notice that the wire right here that goes across and has this circuit in this weird sort of like diagonal shape here for this resistor, well, all that's going on here is it's just blank metal wire. And so what we can do is we can rewrite it in a way that it might be a lot easier to look at, and that would look like this. Okay, cool. So look at this, you see that, oh, this may look a lot more like circuits you've seen before. I just have a resistor, a resistor, a resistor. Well, these are 3 resistors in parallel. So if you recall with parallel resistors, to get the equivalent resistor, what you do, well, really you would say to get 1 over the equivalent resistance, you would add 1 over each of these resistors. 1 over this resistor plus 1 over this resistor plus 1 over this resistor. Now, if these were all different, you'd have to, put those different resistances down here. However, since they're all equal, that makes the calculations really nice. Since these all have a denominator of R, the resistance, which is 4.5, this comes out to just be 3 over the resistance. And now to get the equivalent resistance, because we have that equal to a fraction, we're just going to take the reciprocal of both sides. So we get that our equivalent resistance is equal to R over 3, which is this 4.5 over 3, which if you just chuck that in the calculator, you will get 1.5. So the equivalent resistor is going to be 1.5 ohms. So let me redraw the circuit again. Cool. And we still have the same EMF of 9 volts. Now what's nice here is we have another 2 resistors in sequence. Let me label them now. This is just regular resistor. We didn't touch it. This is the equivalent resistor right here. Now when resistors are in series like this, what's really nice is you can just add them directly. So I'll call this R equivalent 1 for the first step we did. And we're going to get R equivalent 2. And that's going to be just R plus our equivalent resistance. Now here you could either take equivalent resistance as R over 3 and then add these guys as a fraction, and that's what I'm going to do. You could also just throw in the numbers, so it's up to you. My R is still just R. My equivalent resistance here is R over 3. So this is R plus R over 3, which that's 3 over 3 plus 1 over 3 for 4/3 of the resistance. So if we do that, we get 4 over 3 times a resistance of 4.5 ohms. Comes out to 6 ohms. Notice if we just plop the numbers in here, 4.5 plus 1.5, we'd still get our 6 ohms. So now, that's the equivalent resistance for both of these guys. Our first equivalent resistor was these 3. And now the equivalent resistor we just made here is these 2 put together. So let's redraw that circuit once more. There we go. Now the circuits don't necessarily have to get smaller. I just notice I'm doing that because redrawing them over and over, and I don't need as much space to write all these resistors. So this is the EMF, and this is the new equivalent resistance, which was 6 ohms. And this was 9 volts. Now, Okay, so why did we do all this? Well, Ohm's law tells us that the voltage across any circuit component is equal to the current through it times the resistor. So it's actually through any resistor, not any current component. The rules get a lot more complicated for other pieces. So if we have this resistor right here of 6 ohms, notice that all the voltage from this battery here, well, what does it do? It goes around a circle and it goes through this resistor and it comes back. So literally all of it has got to be going through this resistor. So if we want to find the current through it, well, I can just solve this for I, so the current is going to equal the voltage divided by the resistance. So this current right here, I'm going to call it I total, just the current that goes around this small circuit here. That's going to be the 9 volts over the 6 ohms. 9 over 6, that's the same thing as 3 over 2. A volt over an ohm is an amp, and I can write 3 over 2 as 1.5. Okay, so that's the total current. Now what we have to do is we have to start backtracking. We're going to go from this circuit up to this one, and then when we solve this, we're going to go back up to this one, and then finally we'll go back to our original circuit and we'll be able to put everything where it's supposed to be. Well, okay, actually these two circuits are the same, so don't even need to go back to the original one, as it were. All I did for this guy was move this resistor like this. So these are the same. So we have this current here for the circuit down here. Let's move up. So we know that the total current from here to here is going to be 1.5 amps. So the currents are going to be equal when you have resistors in series. The current doesn't have anywhere to diverge or go to different places. It's got to have to just go through this track. So what's going to be different? What's going to be different is the voltages across this circuit. So if I do, let's actually label these now. So let's say this is resistor 1, 2, 3, 4, and now this is resistor 1, and this is my first equivalent resistance right here. Okay, so now let's find the voltage through resistor 1. That's going to be equal to the current through resistor 1 times that resistance. Well, the current through resistor 1 is 1.5 amps, and the resistance is 4.5 ohms. Boop. Okay, throw that in the calculator, 1.5 times 4.5, you get 6.75 volts. Cool, so that's the voltage just across this guy, which notice when we go back to these other scenarios, that resistor isn't touched from here. So that's also going to be the voltage in the original diagram. So I'll just put it right here. Voltage through here, 6.75 volts, and we already know the current as well, 1.5 amps. So we got the first one. Now, what about the voltage across this? So I can do the same thing. The voltage across my equivalent resistor here, which since I pointed to it in orange before, I'll sort of label it like that. That's going to be equal to the current through it, 1.5 amps, times the resistance. Well, this equivalent resistance is 1.5 ohms. Throw that in the calculator. We're getting 2.25 volts. Now, what's really cool about this is notice if I add these two voltages, 6.75 and 2.25, that adds up to 9 volts. Well, what does that mean? Well, all the voltage that this battery has will ultimately be dropped by the time you come back around this circuit. We have 9 volts. I move here to this first resistor, we lose 6.75 volts. And then we move over here to this equivalent resistor, there's 2.25 volts left, and it's all dropped across here. And then there's none, and we go back to the battery. So that's a really nice way to check your work. If you did the voltages correctly, and you go around any loop in the circuit, they should sum up to the total voltage you had to give up in the first place. So now that we have that, let's move up to this circuit. So this equivalent resistor, we found the voltage. It's 2.25 volts. That's what's dropped across it. Now what's interesting is the current through this total equivalent resistor was 1.5 amps, but notice when we move back to this circuit, this wire splits. You can think of the current flowing through here, it reaches this point, ooh, it's now got 2 directions to go. So this current down here is going to go down and circle back around. What about this portion of the current here? Well, it split like this, and now it can go here or it can go through here. And then some of it can go this way and around. So the current should be smaller through here. It should be less than 1.5 amps because it's splitting off and going through these different paths. And then notice that all the current is going to meet up back down here, and they're all going to flow back over here, and we should be back to the original current we had. So it's very similar to water in that respect. That's how it was thought of when it was first studied, is that this is going to go through these pipes and then re-meet back here and flow back around. So how can we find these individual currents? Well, we know the voltage across each one of these resistors. It's 2.25 volts. We also know the resistance for each one of these resistors. It's 4.5 ohms. And something that's really going to save us a lot of time is that for each of these resistors, resistors 1, 2, and 3, let's write it out right here. Resistance 1, well, it's this voltage times this resistance. That equals resistor 2, that equals resistor 3. And since the voltages are all the same, we know that the current through, resistor 2, 3, 4. We know that the current through the second resistor is going to be equal to the current through the third resistor, which is going to be equal to the current through the fourth resistor. And that's going to be this voltage right here, 2.25 volts. So voltage equal over the resistance, which was the same for all of them, over R. So that is 2.25 volts. Divide that by 4.5 ohms. If we do that, we get 2.25 divided by 4.5. We get 0.5 amps as the current through each one of these. So if I label these, the current through each one of these is going to be 0.5 amps. And the voltage across each one of these is going to be equal to 2.25 volts. So this is pretty nice. Now notice how the voltage here was 9 volts. We lose 6.75, and then all that's left is 2.25, and it's all lost here. The current's very similar. We have 1.5 amps of current right here, right? Okay, and now 0.5 of it goes through here, 0.5 of it goes through here, and 0.5 of it goes through here. 0.5 plus 0.5 plus 0.5, that meets back up down here, and we're back up to 1.5 amps. So circuits can be real tricky when you first start doing them because you have to break them down like this, draw a whole bunch of diagrams, and then work your way back. But what's really nice about them is that you always have so many ways to check your work. You can always double check. And so if you make sure to double check as you go, you don't have to worry about blowing up the Millennium Falcon. Everything will be fine.